Yeah, good afternoon to all. So today we will discuss about the transformers working here. Okay. So let me take you to my note. So this is what thing. So transformer, I have already prepared this notes entirely and we will see it. So what is a transformer? Transformer is encoder decoder architecture. Okay. So and what we are going to see today is what happens at encoder side, what happens at okay, and how a context vector is generated at encoder side, what happens at decoder side, and finally how translation happens. So here we are using this transformer for the translation purpose. Okay. So mainly this is Vaswani has defined it. It's in 2017. So let's take this in this sentence. I am doing good now. Okay. And मैं अब अच्छा कर रहा हूँ is the Hindi uh, translated sentence. So this is going to be my X part and this is going to be my Y. So my input and my output. Okay. So two parts will be the training and inference. Okay. So usually we are talking about this training. In training, what it has to do is that it has to look at this sentence and it has to produce this sentence. Okay. So that way it has to learn the weights. So this is what is expected here with this transformer. So encoder side input, we have taken 5 words. Each word is of 10 dimension vector. Okay. So look at here. I am doing good now is a matrix of 5 cross 10 because each word is a 10 dimension vector. So 5 cross 10 is going to be my vector, input vector. So here, Vaswani explained it in a method called, he has used a method called the self-attention to produce the contextualized vector. So instead of using this RNN, recurrent neural network, where it will take word by word, and it is going to take a lot of time to do it in a sequential, okay, to understand. Because it goes I first, then am, then doing, then good. Okay, so this way. But here the Vaswani wanted to do it in a parallel way, so that he wanted to take the get advantage of this uh, GPUs. Okay. So for that one, what he has done is that, okay, so first he has taken query vector, key vector, and value vector. What are these words is that one query in the sense, okay, so for which word you wanted to find out the relation, and key is that, okay, so with what you wanted to do the relation, and V is the value matrix actually. Okay, so original vector. You will understand this one. Okay. Here we have taken the weight matrices Q, weight matrix K, and weight matrix V. So the dimensions are important. Pi cross 10. So to multiply matrix with the pi cross 10, we needed, okay, so 10 cross 10 matrix. Okay, so we are going to take this one. And when we perform this multiplication of 5 cross 10 into 10 cross 10, you will get 5 cross 10 again. Okay, so the same thing you are going to get. Okay, query matrix with the 5 cross 10 and key matrix with 5 cross 10 and value matrix with 5 cross 10. So this is the way QKV matrices he has prepared first of all. Okay. So now what happened is that yes, it's like, okay, so the weights are multiplied with the X part. Okay. 1 second. Yeah. So after doing this one, okay, so he is performing this operation. This is the total formula, softmax of QK transpose divided by root of dk into V. This is the self-attention formula called this scaled dot matrix. Actually here, okay, so uh, positional encoding is there, one more point, and okay, multi-head is there. Those are all small extension to this one only, so nothing to worry. This is the whole concept actually. So QK transpose we are performing. So what we are doing is that one Q is 5 cross 10 and K transpose is, okay, so 10 cross 5. So ultimately I got 5 cross 5 matrix. This is my similarity score matrix. How I am saying it as a similarity score in the sense here, what I am doing is I am finding this relation with this I and am, and this I am doing, and I am good. Okay. So this way, these 5 words uh, or we are finding the relation with the 5 words again. Okay. So that happened with this multiplication actually. This process is actually finding, okay. So matrix multiplication is nothing. We are performing the dot product here. So we are performing here dot product. Dot product will give you the similarity score, scalar value. So I'm going to get 25 scalar values. So that is nothing but the matrix of 5 cross 5. Each word is relation with the other word. Okay. That way you are going to get. So that is the way you are getting this similarity score matrix. And here you are performing the scaling. So to reduce the highest values, and you are performing the softmax to convert them into here. So after performing this similarity scores, after calculating similarity scores, you are performing the scaling, this root dk, and uh, we are going to get the normalized matrix, and that matrix we are calling it as Z. Okay, so it's a size is by cross 5, and you are passing this Z to the softmax. No dimension will change, but they will convert it into the probabilities, and you got this 5 cross 5. Okay, assume it as a EM matrix, and ultimately you are multiplying it with V. Okay, so this okay. So again V is okay. So 5 cross 10. So find 5 same. So you're going to get 5 cross 10. So this is the 5 cross 10 matrix. This is my contextualized vector you got. So this entire process is happening at the encoder side. So once the encoder takes 5 words okay, with each 10 dimension vector, it is going to produce again 5 into 10 dimension vectors only. But now these vectors are contextualized vectors. So what is the difference here is that, okay, usually uh, finding these vectors itself is a big deal with the help of the word to make our low or fast text. These are the very popular mechanisms. Okay. But they are all became the fixed vectors. So the word to vec has generated the word vectors by studying the large amount of data. Okay. And they prepared the word vectors, but they are not contextualized by. Here we are expecting that we want the vectors for the this particular sentence. I am doing good now. Okay, they can't give the this meaning actually. They are static one. Okay, but we are expecting the contextualized or dynamic things. So that dynamism we wanted to get in. So getting the word to make vectors itself is a big deal. And after getting those things, okay, so again capturing the contextual relation among those words is a big deal. So here the Vaswani has attained the great thing. Okay, so this part by doing this thing. Okay, but so by doing a simple dot product operation. Okay, in parallel. Okay, so that's the basically the matrix multiplications he has performed, and ultimately he has found this contextualized vectors. Now this is nothing but okay. So this is a vector. Okay, so of word I and am doing good now. It is only the same thing, but these values, whatever the vector representation is there, those are became more better. So that's the point. Because instead of the word to vector, direct vector, okay, so now these are all the contextual one, they know about each other. Okay, so I know about the am and I know about the doing and doing know about the now. The relation they meet. So this is what okay, so localized contextual information has been reserved or captured here. Okay, so in this one. So this is the output of the encoder part. Now let's go to the decoder part. What is going to happen? So before going to that, what happened is that okay, so this is the encoder. So we have passed I am doing good now, and I got a contextualized vector here 5 cross 5. Okay, this is passed to the decoder, and here it is going to perform the cross attention. What is this cross attention? We will see it. Okay. What it has to do is that this decoder has to take, okay, so this 5 cross 5 matrix, and it has to learn to produce main ab acha kar raha hu. This we have to produce. Okay. Of course, it has to be produced word by word, not all the words. Okay. So producing this word by word, we call it as a auto-regressive mechanism. Okay, auto-regressive. Auto-regressive in the sense, here this ma word is uh, passed as an input to the decoder to produce the up. Okay, and ab is passed as the input to produce the acha. Like this, every word is okay is given as an input to produce the next word as the output. So this is called auto-regressive. This is the way the GPT is works actually. Okay, So that is what we are doing it. Now let's move to the decoder part of the transformer. Okay, so this is decoder. Now here at decoder part, okay, so we are having the contextualized vector and as well as the query vector to be learned. Okay, so this is my thing. That is my Hindi translated sentence. This one. This is my English sentence, which is already encoded. Okay, so the contextualized vectors we have got. Now from this one again we have to get this QKB, but here the query is going to be this. From this one we are going to get the query from this Hindi thing. Hindi sentences. So again, Hindi sentences are 6 sentences, and each word is represented with the 10-dimensional vector. So the matrix became 10 cross 10. Sorry, 6 cross 10. So now here we have to take Q vector for this particular thing, query vector, query weight matrix. So I'm going to take 10 cross 10, and value and K matrices we are taking from this particular encoder part, because we wanted to find out the relation between, okay, so this English and the Hindi. Previously, we have find the relation between among the same sentence. Now we wanted to find out the relation between Hindi sentence and the English sentence. Okay, so this is what we are doing it, and that to be we have to do it word by word actually. Okay, but as of now we are going in a parallel way. So I got a Q matrix is 6 cross 10 when I multiplied 6 cross 10 into 10 cross 10. And here my key matrix 10 cross 10, 5 cross 10 into 10 cross 10 I performed. I got just 5 cross 10 and B is 5 cross 10. I got this. And now what I have to do is that I need to perform the attention meter. Okay, so QK transpose. So here we are calling this as the cross attention. Why we are saying cross attention in the sense here the Q is coming from the different sentence and K we are coming from the different sentence. Previously Q, K, V all came from the same sentence. If Q, K, V vectors are coming from the same sentence, we are calling it as self attention. If they are coming from the different places, that is query is from the different sentence and KV is from the different sentence, we are calling it as cross attention. Okay. So again here, okay, so we are performing Q dot product. Okay, so K transpose 6 cross 10 into 10 into 5. So I'm going to get my Z is 6 cross 5. Okay. So and here the masked attention is happening actually. So this masked attention or we use masked matrix. What is this masked matrix in the sense? We are not going to show all the 6 words at a time. Okay, so we are not going to show all the 6 words at a time. We are going to show first one word only because it has to learn. Okay, so first word. Then based on the first word, it has to learn the second word. So it has to open the second word later. Then 3 words should be open. Then 4 words. Then 5 words. Then 6 words. Last. Okay. At a time, if you show all the words, okay, so it is not going to learn anything. So this is the trick you have to understand. Why this problem in the sense, here we wanted to perform it in parallel. We wanted to do it very speed way. At the same time, okay, so it should be auto regressive. So to achieve this auto regressive one with the parallelization, okay, so we are using this masking concept. Okay. So then we perform this softmax. Okay, so on this masking matrix, okay, uh, then we are going to get the output as a 6 cross 5. Okay. Now we are performing. Okay. So of course here we have done the scale down also we have performed. Then we got, we are taking this V vector. Okay. And this is my output from the QK transpose and scale down and after softmax. So I'm multiplying this V and I got this 6 cross 10. This is the contextualized vector we got from the decoder. Okay. And this matrix is again, okay, so we are going to uh, flatten it and it pass it to the dense layer so that it is going to produce the output of these sentences. Okay, so which one is going to be the highest probability? Of course, may should get the highest probability other than this 6 words. Okay, like this it produces the first word may. Okay, and again this may is going to be taken as the input. Okay, so it is going to be passed here. Now, okay, so now the query is going to become the my word. Okay, so for this my, okay, so we are going to again perform the cross attention and going to produce the next word called the up. Okay, so see this concept here. Okay, so SOS is given as the input and may is produced performing the cross attention. And this may is taken input and again, okay, so this vector is taken, okay, and context vector is taken and again perform the cross attention to produce the upward. Again, this up is passed as the input and it is performed the cross attention with the QK, that KV, okay, from this English sentence. So always we have to consider this English sentence when we are producing the Hindi word, because we wanted to map the relation between the Hindi word and the English word. Of course, it is not happening in a word by word. It is happening in the contextual versus contextual. Okay. This way, what happening ultimately? Okay, so you are performing. Okay, so uh, here this a forward pass is happening. When you did not get the correct thing, so you are going to do the back propagation and you are going to tune the vectors, weight vectors. Where are they weight vectors? Okay, so V and K and okay, so WQ. Okay, so WK and WV. Okay, so these are the my weight matrices. These matrices are going to be tuned. So this way, actually, he has provided, okay, so 16 layers. Okay, so complex thing. So 16 layers of W vector and Q vector and WK vector, WQ vector, WV vector. Okay, so all these vectors are, uh, the weights are tuned. And here the size is also okay, so very large dimension. Okay, so here I took okay, so simple example. Okay, so with the 10 dimension, this dimension can be 700 usually. Okay, so it can be 1000 or 2000. Now it is saying 4000 they are using it. Okay, so the matrix size is going to be very big matrix size. And even sentence also I took here a 5 word sentence. This sentence can be large sentence. Okay, so this way uh, a transformers, okay, so forward propagation, that is from encoder what will be the output you are going to get, and the encoder's output how it is passed to the decoder and how the decoder is going to generate the word by word. So we have discussed here. This is exactly happening with the, okay, so the GPT part actually. So now here, uh, when we break this encoder part, okay, and if you take only the decoder part, which is going to produce, which takes some input and it produces the output. Okay, so that became GPT. So it means that the transformer encoder has become, okay, so one part that is called the bird bidirectional encoder representations. It has given some encodings, okay, and the decoder part has become GPT, generative pre-trained transformer, and it started producing the words, okay, generating the words. So the people, general people are required to, okay, so produce the words. So the GPT got the popularity and word is became as, okay, so representation mechanism. The people who need it, okay, so they use it. So that's the way this transformer has given birth to the two models, and the popular model is GPT. Okay. So this is the working of the regular transformer. Okay, so here we have done, okay, so nothing more than this equation. Okay, so y is equal to f of wx plus b, where this is nothing. Okay, so u and k and b more number he has taken and multiple have taken, and this x is a sentence, English sentence, and this y is, okay, so Hindi sentence. So ultimately we again mapped the thing with the help of this QKB and doing some matrix multiplications. Okay. So here the beauty is that one, the sequential thing is get rid of. So there is no need of this RNN and LSTM and GRU part. Okay, so this entire thing is gone out. Okay, this is written in the paper called the attention is all you need. Attention is all you needed. Okay, so here the why he kept this uh, title in the sense you don't require this RNN and you need not to wait. Why you don't need in the sense RNN will work word by word. First it enters I word, then am, then doing. Okay, so then good, then now. Okay, so it's going to be a sequential one, and you are going to get a H vector, that's a hidden state vector, but it is not going to resemble you. Okay, so the entire information. Okay, so it may not resemble the entire information. So to avoid that one, okay, so this parallel concept is taken, and okay, so the Vaswani has done a great job, and the entire NLP history and the AI history has changed this architecture, and it is applicable for the images and for the audio, for the text, and okay, for what not everywhere the people started working with this transformer because of this parallelism. Okay, and because of this attention mechanism, understanding the context, okay, so of a particular given thing. Okay, so this has changed the entire industry. Thank you. So if any mistakes are there, okay, so please post or comment.